All right, so the three mechanisms, okay. The first one is actually a old friend of ours. If you remember the propensity score measure, I'm sure pretty much every project team has implemented this for your project to figure out how good the utility is. So remember, we talked about propensity score as a global utility measure, right? We stack up the original data set and the synthetic data set. And well, it will be a merged data set of size 2n, okay? And then we used, in our case, I think I recommended using a logistic regression, but actually any kind of classification algorithm will work. So generically, I would just say use a classification algorithm to predict whether an observation belongs to the original data set or the synthetic data set, right? Or doing that kind of binary prediction here. And then we came up with equation 9, if you remember. We returned a summary statistics back then, UP, okay, utility propensity score, which measures overall how close the predicted probability of each observation PI hat is to 1/2, okay? Because we know that the original data set and the synthetic data set, they have the same size. So if the classification algorithm cannot really discern, right, cannot really differing the two data sets, then most of the PI hat will be close to 1/2, okay? Because, well, we know that it is, say, back then it's a logistic regression, so the PI hat is a probability of being assigned to, I guess, back then. Yeah, it depends on how you define it. Say PI hat is the probability, the predicted probability of observation I being like belonging to, I guess, the synthetic data. Then if the algorithm cannot really differ the two data sets, then you will have a PI hat close to 1/2, okay? So we came up with this equation 9, UP, that is looking at the square distance between PI hat from 1/2, right? And then take the average, okay? So high level of similarity between the two data sets gonna result UP to be close to 0. And we also talked about if the two data sets are quite different from each other, then it indicates a well, low level of similarity, and it will be shown as UP to be closer to 1/4. Okay, we talked about this, I think, last time, or at least or earlier, that during those Q&A when each of the group presented the updates, we talked about, well, UP should be bounded above by 1/4, okay, bounded below by 0. Okay, so the pMSE mechanism, so MSE is mean square error, okay? So this is, if you look at equation 9, maybe in other courses you have heard about this term before, it's the mean square error, okay? So the truth is, you can think of like the truth is 1/2, so you're trying to get the distance, right, the error term, PI hat minus 1/2, and it's square, and take the mean, so it's the mean square error. Okay, and P there is just, some people think of it as probability, some people think of it predicted, some people think of it as propensity, whichever, but it's really using equation 9 as you will see, the utility function, okay? So this might sound a little bit complicated, but the general approach of the pMSE mechanism is trying to take it, like turn it into a utility function, okay? But remember, utility function, as you can see, is about the data and about the parameter, okay? So in order to make a utility function based on, right, depending on the data as well as the parameter, one way you can do to make the UP that we defined earlier into a utility function is to take the expectation given theta, okay? So that's what goes into equation 10. X is the private database we're trying to simulate from, right? And X star is the synthetic database, okay? And it is generated from a Bayesian synthesis model, okay? So notice here that X star is just a synthetic data that we can generate. It's not yet private, okay? What we're trying to do here is that we're trying to come up with a utility function, if you remember what we did before, the general flow, right? We're trying to get the utility function. Come back here. Yeah, so what we're doing is proposing different ways to get the utility function, right? But you can see that the utility function is about the original private original data as well as the parameters, okay? And the EM, the exponential mechanism, is only talking about generating private parameters yet, okay? It's not about generating the synthetic data, the private synthetic data. So we are still here in this stage. So that's why when you're looking at the pMSE, you will see that, well, in order to get a good approximation of the expected pMSE, we actually have to generate synthetic data, albeit not private, to make sure that you can get the expected value, which will be able to give you a U, okay? But the utility function, well, is really intermediate in this case, that only if we get the utility function, we're able to compute we are able to get also in equation 11, as you can see that the sensitivity delta U is bounded, so we're able to compute and simulate, right? Simulate theta hat. Okay, so this is still just about theta hat. So when you do that in practice, what you do is you get a U x theta based on the expectation of the pMSE. Okay, you get that, and then you get the delta U there, and then you're able to sample from the exponential mechanism. Okay, so that's what we mean by all of the three methods, pMSE being the first one, is trying to propose ways to come up with the utility function, okay, that is also related to the sensitivity, right? Once you have a utility function, you'll have a delta U, and then you're able to draw, as we show you here, from the exponential mechanism here, okay? So we're still in the process of getting what U is, what delta U could be, and then we can make theta to be theta hat, which means that the non-private parameters theta based on the EM will start to become private. Okay. All right, so that's the first one. Okay, like I said, complicated to implement. A general idea seems straightforward, but there's a lot of theoretical proof behind it, why this works and all that. So, and I also unfortunately do not really have a demo here. The second mechanism based on the EM is the posterior mechanism. Okay, so this is probably our best friend. And in a sense that, yeah, so even though earlier here, this is, I still sort of think of this as Bayesian approach in a sense that you still have a Bayesian synthesis model in your F in the first place, right? But the way to construct U is not so much Bayesian, right? It is just the propensity score, right? Expectation propensity score, okay? And however, the second mechanism here, like I said, is much more Bayesian focused, okay? So they proposed a couple of years ago to use the log likelihood as the utility function, okay? So that's what we write in equation 12, okay? So utility function about X, okay? And it's the log likelihood, and we write it here as a product and then take the log, because we know we usually always assume that observations are independent from each other, right? So the joint likelihood is whatever after the log, right? Theta, again, is the generic notation for all of the parameters, and then we take the log in the end, okay? So they propose to use the log likelihood as the utility function in equation 12, and they also show that the sensitivity of this particular utility function will be bounded by this delta, okay? It's called the Lipschitz bound. Okay, don't worry about the term and all that. The caveat here is that, well, even though it's bounded above, okay, by delta, the Lipschitz bound, sometimes it could be infinite, okay? When you have actually even simple models like normal, exponential, Poisson, geometric, when you use that, meaning that when you use a log likelihood, like your likelihood function F is like normal, exponential, Poisson, geometric, you won't be able to find a bounded delta, okay? So that's the caveat, and that's why when they proposed it, even though it's really nice theoretical work, I think the limitation there is that a lot of times the models they can only propose like super simple models like betas or beta binomial, that kind of work, to make sure that they can get a bounded delta in equation 13 so they can make it work, okay? But once you have it, what you do is, well, now you can draw private parameters theta hat from this equation 14, okay? So equation 14 is almost the same as before, except now I replace the U, the utility function, with the log likelihood function, okay? So in practice, right, if you imagine like in practice what you're going to do, you will have to find the log likelihood function, right, from the data set that you're working with, and then you plug that in order to make your theta hat private, okay, from the EM, right, the exponential mechanism. And they also prove that if you can satisfy all of this, the posterior mechanism achieves a 2 delta, right? 2 delta equals to epsilon. So epsilon, remember, still is the privacy budget. So privacy budget will become 2 times delta, guarantee for each posterior draw of theta. Okay, so that's their main contribution to lay out the foundation of thinking about, okay, how can we, from a Bayesian perspective, to figure out what will be a suitable candidate for the utility function. They propose the log likelihood. Okay, the proposed log likelihood, they also show that it will be bounded above, the sensitivity of it will be bounded above the Lipschitz bound. Okay, obey can be infinite in some simple cases, but it is not infinite in some other cases, and that's how they did the demonstration, I think, in their paper. And also, very importantly, they show that once you can make all of this work, your privacy budget, epsilon, will equal to 2 times delta. Okay, so meaning that if you have a bounded Lipschitz bound, if delta is bounded, then you're able to show that if I am sampling my theta hat from equation 14, I can satisfy epsilon equals to 2 delta. Okay, so that's their posterior mechanism. Okay, the third one is the one that I worked on with some collaborators. We are trying to generalize the posterior mechanism to make sure, or to ensure, that the Lipschitz bound delta is bounded. Okay, it is not infinity, it's less than infinity. Okay, the way that we did it is to add weights in the likelihood function. Okay, so equation 15, as you can see, is still the log likelihood, right? But it's not exact likelihood because we put a weight, okay, in the exponential function. Okay, so what we're really doing, if you imagine what we're trying to do, is we are getting a alpha I for each record. We have a weight, okay? How to compute it, I put it there in equation 16, but don't worry too much. The general idea here is that we're trying to put a weight in the likelihood function that we're able to make the Lipschitz bound delta later to be bounded. Okay, we show why that works, okay? And the way to do it is to add a weight in the exponent of the likelihood contribution. Okay, so once you add weights like this, it's not like the whole thing in equation 15 is not called as the log likelihood anymore, because it's not the likelihood, it's the exponented likelihood. And in the literature, people call this pseudo likelihood. So sounds pretty funny, right? It's pseudo likelihood. It's not likelihood itself. It's pseudo likelihood because we have added weights in the exponent to each of the likelihood contribution. Okay. One thing you can think of this is that, well, so the general, let me see. Okay. Yeah, so in general, when you don't have that alpha I, it is the regular likelihood, right? Regular log likelihood. And alpha I, so when you don't have alpha I, or if you set alpha I equals to 1, you go back to the log likelihood, okay? So the weighted version of the log likelihood, or the pseudo log likelihood that we call it here, or log pseudo likelihood, is trying to figure out, or using weights to make some contribution more important than the others, okay? So one thing, if you imagine, like if I have a record xi that I wanted to have no contribution at all to the joint likelihood in equation 15, what I do, I set alpha I to be 0, because anything raised to the power of 0 is 1, right? So I have certain portion of the distribution that I don't want them to contribute to the likelihood function. I can set alpha to be small, right? If I set alpha I to be 1, it goes back to the full contribution, right? So you will see, well, you wouldn't see, but let me just tell you, in equation 16, the way that we set this up is that, well, the alpha I is going to be between 0 and 1. Okay, we're trying to downweight, we use the word downweight, certain records, which we don't want them to contribute too much to the log likelihood. We downweight them by using small alpha I, say alpha I goes to 0 or close to 0. If we still want to keep its contribution, okay, at its original, then we will keep alpha I, say, at 1 or close to 1, okay? All of the motivation coming to this, which I will show you in the simulation study results I show you, is that we didn't, when we first worked on this, we were not thinking about differential privacy per se, okay? What we're thinking is, okay, when we have what you're actually doing exactly right now in your project, that once I have developed a synthesizer, okay, synthesis model, I synthesize my data, and then I can get attribute or identification risk. Let's just say identification risk. I can get for each record an identification risk as a probability. So if some of the records are having really high identification risk, we want to mask them a little bit more in the synthesizer, okay? Because we want to provide more protection for those high risk records. For records with low risks, well, we just let it go, like let them be whatever they are. So we're trying to use this weights in an idea that is actually tied to the identification risk, okay? So we did a work like that earlier. And then we realized, okay, actually the pseudo likelihood idea can also be turned into differential privacy. And what we did is we showed in equation 17, that's how you're gonna use it as a utility function. And we also showed that it's gonna be bounded by this delta alpha, and we make sure that delta alpha is bounded, okay? So all sounds a little bit vague, but in the end, like I said, we are able to simulate and draw a private parameter draw theta hat from equation 19, okay? So this is where we replace the u, the utility function, with the log pseudo likelihood here, okay? And just like the posterior mechanism, the pseudo posterior mechanism also achieves a 2 times delta. In this case, we labeled it with alpha because it's the weighted version. Okay, so just to give you a sense, I only provided, included one photo here. This is when we simulate data from a Poisson distribution, okay? And we're trying to estimate the mu, okay? So remember, or lambda, whichever you use. Poisson has only one parameter, okay? We simulate data from it, and then we estimate how the rate or the mean parameter is being estimated. So this is a synthesizer, okay? This is actually just a Poisson synthesizer, nothing about DP, okay? Nothing about differential privacy. So I know some of you in your project are doing some kind of Poisson regression, okay? This is actually even less complicated than a Poisson regression. It's just a Poisson model, okay? We use a Poisson model, like lambda, all of the conjugate things that we do. So this is the unweighted model, okay? You can see that while we simulate mu, the Poisson data that we generate data from this model. Okay. And now we're trying to estimate how good the mean variable is being estimated. So a little bit underestimated, as you can see. You should be close to 50, right? Like right around there. But overall very close, because if you look at this, it's actually 49, it's not 40 or something. But anyway, that's the unweighted model. This is any Bayesian synthesizer, okay? This is, I should say, this is the particular Poisson model that we estimated, okay? And the weighted version that we did, that I show you, the pseudo posterior, is this one, okay? And the posterior the posterior mechanism, the one earlier that I show you, is this one, okay? So this CW is another method. I won't bother you with the detail, but I want to show you here is that we showed in this work, okay, that the regular posterior mechanism, even though the overall estimate of mean is not that far from what the unweighted is doing or the truth, but it's having a larger spread, as you can see, compared to this and this, okay? So again, I wouldn't bother you with too much detail about all of this, but I just want to show you some of the work that people in this field have been doing, figuring out how to come up with your, let me come back here, how to come up with a good utility function, right? A utility function that is bounded and then can provide the differential privacy definition, can satisfy the differential privacy definition. All of this are pretty much rely on the exponential mechanism, okay? Because again, it can make a non-private mechanism into a private, and most people in this field have been doing that in terms of making the parameters private from the exponential mechanism, okay? And then use the fact that any functions of the differentially private parameters will be private, differentially private. So they're able to justify that the synthetic data generated from private parameters will also be differentially private. Okay, so that's all I prepared actually, and I should mention that didn't get too much chance to I guess open up to discussion and all that, but I mean, given the time, we should have about like 5 minutes if you have any quick comments, questions, or concerns about what this is doing, and we will have time to address that before we move to the presentations. Yeah, Sarah?
So I had a question about your resultant violin, or the violin plot. So is it good that the spread is like not as high if it's closer to the, like, why is that a good result?
Right, so yeah, I closed it already, but what Sarah is referring to is I show you on the far right that is a wider spread of the estimation of the mu parameter, okay? So when we say that, so the thing is, the unweighted, the first one that we show is the synthesizer, okay? So the synthesizer is always having the highest utility, because anything else that we make, like we added the synthesizer in something, weighted it, or doing something else about it, is only trying to achieve differential privacy, okay, but is at the cost of satisfying its utility, okay? So that's why if you have, well, if your unweighted synthesizer, non-private synthesizer is achieving utility as good as what we see, so you can think of that as a gold standard, right? That's why we say that the other one is not good. But also in general, whenever you're, I guess, doing this kind of work, you want to have estimation that is having less spread, right? You want to have less uncertainty in general. So that's another thing about it, why, well, our proposed method is slightly better than the other one.
Thank you.
Anything else? Yeah, so you will see that how complicated. Well, one thing I think is that the field is being developed and fast growing, but also it does assume a lot of knowledge. I mean, when I talk to others that like we're having a data confidentiality course at master, people are saying, it requires too much. Like people need to know Bayesian, they need to know this, need to know, you cannot teach undergrads this, and blah, 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 blah. But anyway, well, I mean, what I was thinking is, well, you all took Bayesian with me, so I think we have the general foundation, and then we gradually build up all of the work that we have seen, as well as you're doing for the synthetic data portion. So to me, that is, well, model-based, right? And then also think about how Bayesian methods can be implemented there, use them as synthesizer. But anything now, like for the last, I guess, 3 or 4 lectures that I show you about differential privacy is much more theoretical, okay, much more complicated in the sense that I would say, I don't know, I definitely would think that maybe in the future, next year or the year after, when I teach this intensive again, I'll be able to ask students to do projects on differentially private synthetic data if possible. But that's another thing, that the field is being developed, people are making progress, but it's definitely very, I wouldn't say very, but definitely to some degree inaccessible to undergrad students, or even for researchers. Like it took me a long time, I think, I count maybe almost like a year by now, just to get more into differential privacy, get into the literature, and then getting to understand all of that. So don't feel frustrated. I just want to show you that, well, the field is being developed. A lot of researchers are putting effort and energy into this. So maybe in a few years, more accessible methods will be developed, and then well, maybe next time when I teach the course, well, the 3 methods that I mentioned to you just now, I will be able to just do some quick demos in class instead of just telling you all, okay, this is how people are doing this and all that. But I hope to show you such an open-ended questions here, the utility function, how people are thinking about it, and then of course how to design it, and then how to make it work. I think is definitely good research directions if you ever get into this or curious about them. Okay. All right.